Assalamu alaikum. Let us continue with the last lecture. We were discussing about the per unit values, how to calculate different per unit values. So here we'll take up small numericals first, and after that we'll come to the question. The question is here: if a resistance, if the actual value of the resistance is 5 ohms, find its per unit value for the base kVA of 10 and base kVA of 11. So here the kVA rating is 10 kVA and the kV rating is 11 kV. It's not actually rating, it's a base value, reference value. So first we'll calculate the reference value of the impedance. Then we will divide that impedance to this 5, we'll get the value. So this is given by VB square by SB. 11 into 10 to the power 3 whole square divided by SB is the 10 into 10 to the power 3. This comes out to be 121 into 10 to the power 6 divided by 10 into 10 raised to the power 3, that is 10 raised to the power 4. It comes out to be 12100. When we divide it, we will get this simple value. It is very simple. Now coming to the another numerical, this is regarding the transformer. Here also we will numerically prove that the per unit value referred to primary or referred to secondary will be same. It is given here a single phase transformer is rated as 25 kVA, 110/440 volts. That means primary voltage is 110 and secondary voltage is 440. If the leakage reactance of the primary, actual value of the primary leakage reactance is 0.04 and actual leakage reactance on the secondary is 0.10 ohms. This is actually in ohms. We need to here show that ZLPU is equal to ZPU referred to low voltage is equal to ZPU referred to high voltage. That means we need to calculate two values of the per unit values of the Z referred to primary and referred to secondary, and we have to show that these are equal. Here you can see A with respect to the primary is 110 by 140, 440, that is equal to 4. A is equal to 4. SP will take this as our base kVA, that is the rating of this, and here first we will calculate Z per unit with respect to the primary voltage. Primary voltage is 110, that means our VB is 110. So these two are fixed. So we can calculate ZB. ZB is equal to VB square by SB, that is 110 square. Here it is volt, that means there will be no 10 to the power 3 or K, divided by 25 into 10 to the power 3 because this is 25 kVA. It comes out to be 0.484 ohm. Now we'll first calculate the actual value of the ZLV, the total impedance referred to low voltage. It will be equal to low voltage reactance plus the high voltage reactance referred to primary. The high voltage reactance will be equal to, it will be 0.04, that is the low voltage reactance, plus high voltage reactance referred to primary, it will be multiplied by A. A is 1 by 4, it will be equal to 1 by 16 into 0.1, it comes out to be equal to 0.04625. So to get the per unit value of this impedance referred to primary, it will be equal to the actual value divided by the base value. Actual value is 0.04625 divided by 0.484. It comes out with this value, 0.09558 per mm. Now we'll do the same thing. First we'll calculate the total reactance referred to secondary. It will be this value referred to secondary. That means it will be equal to now its A will be now equal to 4 square into 0.04 plus 0.1. It is actual value of the secondary winding, so it comes out to be 0.4. Here VB will change. This is the important thing that I have told you in the last class, that we need to change the VB, that is base value, from primary to secondary. In that case it will remain the same. This Z per unit will remain the same. So base value here is 440 volt. So ZB will be equal to 440 square divided by 25 into 10 to the power 3. It comes out to be 7.744 ohms. So total impedance, now impedance referred to primary, secondary will be now, per unit impedance referred to secondary will be now, that is this value, which one? This value divided by this value. If you do this, it comes out to be same. you'll see that this value and this value is same. So here we deduce that whether referring to primary or secondary, we will get the same per unit value. Only thing provided that the base value of voltage will change from primary to secondary. If the base value of the primary is, let us say V1, and if the rating of the secondary is V2, we have to take that V2 as the base value now. Now sometimes we are asked to find out the percentage, or we are sometimes given the reactance in terms of percentage value. The percentage per unit are related simply by this relation, that is percentage will be equal to 100 into per unit value. This we know already, but since it is regarding to this our network, we should know this also. A percentage is equal to 100 into per unit. Sometimes you may ask to find out the value in percentage and sometimes in per unit. Per unit we know, but percentage it is simply you just multiply per unit by 100 value. This is a simple numerical. Now coming to slightly practical numerical, in which we may be asked to find out the per unit network of some single line diagram. So we need to be slightly careful. Here the question reads like this: draw the reactance diagram using the base as 100 MVA to 20 kV in 50 ohm line. The rating of the generator, motor and transformer are given as: generator rating is 40 MVA, 25 kV, X double dash is equal to 20%, that is 0.2 per unit. I have written it as written for you. Now you are familiar with this, that percentage is nothing but 100 multiplied with per unit. Per unit will be percentage divided by 100. So in terms of per unit it will be 0.2 per unit. Similarly, motor has 50 MVA, 11 kV, X double dash is 30%, that is 0.3 per unit. But this is again these value, that means this value, since it is given in per unit, it is calculated on the base of 40 MVA and 25 kV. Similarly, for this case, it is always calculated on its own base, own rating. That is this. That is 0.3 will be on the base of 50 MVA and 11 kV. Similarly, transformer T1, 40 MVA, 33 kV by this 220 kV. X is equal to 15%, is 0.15 per unit. Again, this is calculated on these two bases. Similarly, transformer T2, it is 30 MVA, 220 by 11 kV. X is 15%, that is equal to 0.15 per unit. Usually you will see that the transformer, all the transformers, I have not written over here properly, they are always written high voltage to low voltage, whether it is connected from primary side low voltage and then on secondary side high voltage, but it will always be written like this. But here for your convenience I have written is 33 by 220, that means here will be 33, here will be 220, then 220 by 11, that means here will be 220, here this side will be 220, this side will be 11. So I hope you understood this. Now here it is given that you have to choose the base as 220 kV and 100 MVA. Sometimes you may not be given the base, you have to choose yourself. You can choose randomly base as you wish, but since voltage rating will be almost same for every this equipment, but MVA rating will definitely change. So it is advisable to take the MVA rating of the highest equipment as base. Otherwise it is your choice whatever you take, but it is advisable to take the base MVA as the highest MVA of any equipment present in this. Since here if we are not given the base MVA, we may take the base MVA as 50 MVA, the MVA rating of the motor. Now coming back here, so first we'll divide into three zones. One zone is the primary of this transformer T1, another zone is the secondary and primary of this transformer, another zone is the secondary of this transformer. The primary of it is given as 220 kV in 50 ohm line, that means 100 MVA and 220 kV is given in this zone, that is the secondary of this and primary of this. In this zone, I have shown it over here, dashed by dashed lines. In this zone, the rating is like this. As I've told you, since base is given, this MVA base will not change from here to here. It will always remain the same. This zone, and this zone, it will remain the same. But this KV base changes. It depends upon the transformer ratio. For example, its transformer ratio is 220 by 33. That means here it will be 220. The base here is 220. Here it will be 33. Here the transformer ratio is 220 by 11. Here the base is 220. Here it will be 11. So it means we have three zones. Zone 1 to the right left of this transformer. Here the base will be 100 MVA and 33 kV. And zone 2, that is this zone, here the base will be 100 MVA and voltage will be 220 kV. And zone 3 to the right of this T2, the base will be 11 kV and MVA base will be 100. So MVA base will not change, voltage will change according to the voltage ratio of the transformer. So first, for the zone first, SB is 100 MVA, 100 MVA, VB is 220 kV. This is for zone second, sorry, because it is given 220 for the line. So we'll calculate ZB for zone second. It will be equal to VB square by SB. It is equal to 220 square by 100. That is equal to 484 ohms. Because 220 kV square, this kV square will be equal to M, 100 M. That M and N will cancel out. This comes out to be 484 ohm. So this is the ZB in this zone. Now since we are given the values of generator or transformer in this zone on their own basis, we need to use the change of base formula to calculate the new per unit values on the given basis. For example, xg per unit, the value of the xg is given as 0.2, but its base is 40 MVA and 25 kV. We need to change it, and we need to change its base to 100 MVA to this 33 kV, because here the base will be now 33 kV as per this transformer ratio. So it will be equal to SB2 divided by SB1. SB2 here is 100, SB1 is 40, into VB1 by VB2 whole square. VB1 is its own voltage rating, that is 25, VB2 is 33, the transformer ratio rating, the new base. So it comes out to be J, because it's a reactance, 0.27287 per unit. I have written over here, it is 0.27287 per unit. Let us zoom it a bit. Similarly, xt1 per unit will be equal to 0.15 into 140, 33 by 33 square, because its rating is already given for 40 MVA and 33 kV. Here we are not changing the base kV, it remains the same, only as per the base MVA it will change. So it comes out to be 0.375. I have written here like this, 0.375 G. Similarly, for this XTL per unit, the transmission line, it is not given in any per unit, it's given in ohms, its actual value. Its actual value is 50, and we have calculated its ZB in its own zone. So it will be equal to 50 divided by 484. It comes out to be equal to J 0.1033 per unit. XT2 per unit will be equal to 0.15 into 100 SB2 divided by SB1. It's the new base and old base is same, so it comes out to be 0.5. I have written over here 0.5 per unit. And the last one is, I have written here the base values of this. VB is 33, VB is 220, VB is 11. So here base value will be now 11, not 33 kV. So here 0.3 into 100 by 50, because it is given as the reactance of the motor is given as 0.3 on base MV 100 and kV 11. So in that case, its old base and new base kV is same. It's not make any effect, but as new base is 100, it will change its value to 0.6. So voltage, that is the terminal voltage at this point. The terminal voltage at this point is given as 25 kV. That's why I have written at VG per unit. It is 25 kV, but our rating, our base value is 33 kV. So its per unit value will be equal to 25 with 33, that's 0.7.6 per unit. And VMPU, that is the terminal voltage of the motor at this point, will be, since its earlier basis, its actual rating is 11 kV and our base is 11 kV, so it will be equal to 1 per unit. So here it means our circuit is complete now. This circuit is ready for any analysis, whether fault analysis or any other analysis. We will see that after completing this. But the per unit reactance diagram for this single line diagram is given by this. I hope you have understood this. Let's come to the new topic. It is a symmetrical fault. Symmetrical fault means, as the name suggests, it results in the symmetrical currents. And it is because the fault involves all the phases. Symmetrical fault, in other words, will be a three-phase fault, or sometimes three-phase to ground fault. You will see that when three-phase to ground fault occurs, and all the phases are close to each other and the currents are balanced. We know that there is no neutral current. So the three-phase fault or three-phase to neutral fault, three-phase to ground fault are same, because in both the cases there will be no current through the neutral, and the fault current that is flowing through the phases will be balanced. They are equal in phase and they are displaced by 120 degrees from each other. That's why they are balanced current, and this results because of insulation failure and flash were initiated by the lightning stroke, as I have discussed in the first class. So these are the two main reasons of three-phase fault. It results in huge current, and usually circuit breakers are designed on this kind. Before explaining this graph, I will tell you some basics of the synchronous machine. All the machines you know are the constant flux machines. It is because wait a minute. We know that all our machines are constant flux machines, and it is because this voltage, that is induced voltage, is given by this relation, that is V is equal to 4.44 F phi N kW, where F is the frequency of the supply or frequency of the generation, phi is the flux generated, N is the number of turns, and kW is the winding factor. So for a constant voltage and constant frequency, which is usually the case, we always want voltage and frequency to the constant, and these two are constants by the geometry or by the construction. So when these two are constants, you'll see that flux will be constant. When flux is constant, our machine becomes constant flux machine. This is true for every machine, but I want to apply this to synchronous machine. I will come back to this diagram. So when V and F are constant, flux will be constant. Now coming back to this diagram, this is actually a fault current. When a fault occurs on our synchronous generator, I can show it over here. It will be something like this. You will see that this current IA, this will be lagging to this EF by 90 degrees. This will be lagging to this EF by 90 degrees. And if you remember, if this is EA, this will be field flux. And because of this current, this is IA, this will be phi AR. You can see from here, we know this is the relationship between EA and phi F in case of synchronous this machine, that EA is lagging to this phi F by 90 degrees, and they are related to each other like this. When this fault occurs, this current has got very high magnitude and it is lagging to this by 90 degrees. It means it is demagnetizing in nature. So this was very important point. Since this results in demagnetization, this flux will reduce. This flux will reduce. Since this flux will reduce, but our machine are constant flux machines. Our machines are constant flux machines. It will try to make somehow this flux constant. So in the earlier period, you can see the envelope of this current is very high. It will draw the current through the damper winding as well as field winding, so that the total current will increase. When the damper winding and the field current winding increases, total flux will increase. And in this case, it will try to make the flux equal to the actual flux. So that is why you will see that the two currents will flow through the damper windings and field windings, resulting in the increase in flux. You will see the envelope of the current will be more. But as you have read that field winding has very high inductance and damper windings have very low inductance. And we know the time constant will be equal to L by R. Field winding will have higher time constant as compared to the damper winding time constant. What I mean to say is that since such kind of currents are transient in nature and they depend upon this time constant, the current in damper windings will decay very fast as compared to current in the field winding. So after completely decaying the damper winding, there will be the transient which will flow through the uh, field winding. They will continue to flow, and after the flux has sustained its value, you will see that that current through the field winding will also reduce to zero, and finally the normal current, that means normal current will flow through the system, and that normal current will result in the normal flux of the system. What I mean to say is that our equivalent circuit of the synchronous machine in initial period will be like this. It will be the leakage reactance in series with the parallel combination of this damper windings, this armature reaction, and field winding reactance. So these three will be in parallel because this damper winding will also carry the current, armature reactance will also carry the current, this field winding reactance will also carry the current. So this initial period is known as subtransient period, and XD dash is the total reactance that is provided by the synchronous machine in this period is known as subtransient reactance and denoted by XD dash, and it is equal to XL plus XAR in parallel because they will be now parallel, XF field winding, and XDW, that is damper winding. So you will see that since this I have explained that the time constant of damper winding is less than time constant of field winding, and this ID dash will be equal to this OC. OC is this envelope here to here, OC divided by root 2. This ID will be the RMS value of the initial subtransient current. ID dash will be the initial RMS value of the subtransient current. This is the current that flows through this synchronous machine in the subtransient period. Since after this initial subtransient period is over, the current will still flowing through this field winding, and the circuit will reduce to like this. And you can see here this value of reactance will be equal to XL plus the parallel combination of XAR and X field winding. You can see this value or we can say XD dash will be greater than XD double dash. That's why in this case the current will be slightly lower. So that's why we have shown it. Its envelope will be like this, and its value will be equal to OB divided by root 2. ID dash will be equal to OB divided by root square root of 2. That is the RMS value of the current in transient period. It is equal to EF divided by XD dash. This will be equal to EF divided by XD double dash, RMS value of the this sub-transient current. And finally, when all transients die out, we have a steady state current. That steady state current will flow through the leakage reactance and armature reactance, and simply XD will be equal to XL plus XAR, that is the synchronous reactance, which you have already studied in your machines class. And you can see it from here. This XD will be greater than XD dash. That XD dash will be greater than XD double dash, and ID, that is the steady state current, will be equal to EF by XD, and or that will be equal to this OA. This should be your O origin, OA divided by root 2. Maybe I have forgot to write it, but it is like that. It will be equal to OA by root 2. So this is about the short circuit of the initial of the synchronous machine, and these are the different values of the currents and impedance in different periods. So their range will be, this XD will be 1 to 2 per unit, 2 per on their own basis of the generator. So XD dash will be equal to 0.12 to 0.35 per unit, and XD double dash will be equal to 0.1 to 0.25 per unit. I hope you understood this well. So next talk will be discussed in the next class. Okay, thank you.